Okay, let's continue with more examples of finding extreme values and finding critical points and everything that is needed to solve these simple optimization problems. So let's try to find the extreme values of f of x equals 2x cubed minus 9 x squared plus 12x. And we're asked to do that on two different intervals. So the two separate problems is the same function, but there are you're asked to find the extreme values on 0, 3 and on 0, 2. A very important point here to make is that finding extreme values of a function f is strongly dependent on the interval in which you're doing the analysis. Of course, if you change the interval, the endpoints are changing, so you need to check now the two different endpoints, and also some critical points of f may fall outside of the interval which you're minimizing, so they are not candidates for extreme values on that interval. Okay, so I mean you just have to be careful and do the analysis so that taking this into account. So whenever you find critical points, make sure that your critical points are, in this case, in between either 0, 3 for the first question and between 0 and 2 for the second one. And you also have to check out the different endpoints. So let's try to do that. So solution. So first look at for the case when we are maximizing things in between and finding extreme values in 0, 3. So endpoints. First, endpoints. Remember, endpoints f at 0 is 0. So 2 times 0 cubed minus 9 0 squared plus 12 times 0 is 0. F of 3 is equal to 2 times 27. 3 cubed is 27 minus 9 times 9 times 9, so 3 squared, and plus 12 times 3. This is 54 minus 81 plus 36. So this will be equal to 9. Okay, so this is what happens at the endpoints. Now we need to look for what happens at the critical points. Critical points. And so we look for points, in this case again, we'll look for points such that f prime of x is equal to 0, because f of x, being a polynomial again, is differentiable everywhere. So there are no points in this case, no points where f prime is not defined in this example. So for this example, in this case. Okay, so let's differentiate f of x. So f prime of x is equal to 6x squared minus 18x plus 12, and we set that equals 0. We see that, we have a common factor of 6. So this is equivalent to, we can factor by 6. So 6 times x squared minus 3x plus 2. And we can divide by 6 on both sides. So this is the same as x minus 1 times x minus 2. We factor out like that. I mean, minus 1 minus 2 is minus 3, and multiply to give you 2. So the critical points x equals 1 and 2. And we record the value of f at 1 and f at 2. So what is f at 1? Is 2 minus 9 plus 12. Okay, so 5. And what is f at 2? F at 2 is, let's say, 2 times 8 minus 9 times 4 plus 12 times 2. So 16 minus 36 plus 24 is equal to 4, I believe. Yeah, okay. So we have, so let's put all the values together. The f 0, which was equal to 0 for the endpoints, then f at 3, which was the endpoint, which was equal to 9. So these were the endpoints, so corresponding to the endpoint. And we have the critical points. Critical points here, f1, f2. 1 gave us, f2 gave us 4, and f1 gave us 5. So f3 gives us the maximum value, so this is the maximum value. And f0 gives us the minimum value, the absolute minimum value. Five and 4 are not the extrema here. So neither one of the critical points gives us an extreme value. Now, but this is when we're looking at the function on the interval 0, 3. So what happens now when we'll look at 0, 2? So here we only have one critical point, one critical point. You can consider 2 to be a critical point, even though in principle, you only have one side to take derivatives on, to take the limit on. But in any case, so we don't have 3. So this changes things a little bit. So we already recorded, we already found that the critical points were 1 and 2. And if you want to consider that even in this close interval that barely contains 2 on just on one side, it's fine. But in any case, we still needed to incorporate that into the analysis because it's an endpoint now. The endpoints are now 1 and 2, 0 and 2, right? So these are endpoints. F at 0, which we already computed, 0, and f at 2, which is equal to 4, right? 3 is no longer an endpoint. It doesn't belong to the interval, right, on 0, 2. So this is what happens in 0, 2. And the critical points, there's no need to write down what f2 is again, but f of 1 is equal to 5. 1 is in 0, 2. Is in 0, 2. And now the situation changes a little bit. 0 is still the minimum value in this interval, here, but 5 is now our max value, and it's coming from a critical point. So again, keep in mind, so whatever you do when you're asked to find extrema, you need to record what happens at the endpoints, then find the critical points by taking derivatives that are equal to 0, finding the points at which this happens and recording those values, and possibly also the value of f at points where f is the derivative is not defined. Put all those values in a list like this one over here, and then see which one gives you the largest value and which one gives you the smallest one. Okay, and that's how you do it. And remember that the problem may be sensitive to where you're in one interval or another, as we saw here. Here, when we were finding extreme values of f in between 0 and 3, we found that the mean value was 0 and the maximum value was 9, and they were achieved at the endpoints, not at critical points. If instead we looked at what happened between 0 and 2, we found that the mean value was still achieved at an endpoint, which is f of it was 0, while the maximum value was achieved at a critical point, which is f of 1 equals 5. Okay, so we'll continue with more examples in the next video.